Alright, so here we are back with our tutorial, and here I'm going to teach you how to minimize functions that has don't care conditions within them. Okay, so okay, fine. So let's just first consider a function. Okay, let me just call it okay, small f, and this is equals to sigma small m, and the elements are 1, 5, 6. And then you got 12, then 13, 14. All right, now these are all the functions which have their which are really necessary to be taken into account, and they are not the don't care functions. Okay, now the don't care functions are kept into another group whose a function is just denoted with the small d symbol over here. So you got here 2 and 4. So here 2 and 4 are the don't care elements. Okay, so I'm just gonna write that over here. So these are the don't care elements of the function concerned. All right, so well, this is our function, and what we need to do is, as a problem statement says, alright, here it is. It says that reduce this function small f, okay, this thing that I've just stated right over here, and we'll implement the reduced expression. Okay, that's what we're gonna realize from the K-map and in universal logic. Okay, so we gotta find out first the reduced expression out of this particular function, and then finally map it using universal logic, or rather circuitry designed using NAND or NOR gates, that are the universal logic gates. Okay, so let's just move on to the problem over here. So first we're gonna need a K-map. Okay, the question is what should be its capacity. So if we just take a look at the function once again, so we can see that there the highest element is 14. Okay, so the cell, so we basically require a 16 cell K-map, so which means we require a 4x4 K-map once again. Okay, so in order to construct a 4x4 K-map, we'll be needing a bigger square. Okay, so there you go. We have a bigger square over here, and now it's gonna have 4 rows and 4 columns. So here that's row number 1, that's 2, and finally the third row. So again, column number 1, and then 2, and there you go, 3 and 4. So once again, we just put down the binary data over here. So 0 0, okay, 0 1, 1 0, and 1 1, and finally for the rows 0 0, 0 1, 1 0, and then we got 1 1 over here. All right, now the cell numbers. So 0 1 2 3 4 5 6 and 7. All right, so now then comes 8 9 10 and 11, and then you got 12 13 and then 14 and 15 finally. Okay, so now you can see that at the row and the row and the columns are designated with 2 values of variables each, so it's going to be a 4 variable K-map. So let's just for the rows take the variables AB, and for the columns let's just take them as CD. Okay, that's better. So now let's just take a look at the function. So we have here the function says that the elements 1 5 6. Okay, let's just put them down in the K-map. I'll use a different color. Okay, so 1 5 6. So there you go. And since it's a SOP expression, just take a note of this thing. So it has a sigma sign over here. So it's a SOP, that's the sum of products function. So whenever we have a sum of products function, then a complementary quantity is represented with a 0, and a non-complementary quantity is represented with the symbol 1. Okay, so if we got A and it's a non-complementary quantity, so we'll use a 1 in order to represent A if it is present in the function. Otherwise, we're gonna if we have a bar present in the function, then we're gonna designate that with the symbol 0. Okay, so with that said, we could just go straight to the K-map. So we have the elements 1 5 and 6 first. Let's just number them first. Okay, so we gotta put 1 in the place of 1, 5, and 6 numbered cells. So there you go, we did it. So the next elements are about 12, 13, and 14. Alright, so let's just take a look. Where is 12? Okay, so 12, 13, and there you go, 14. Fine, so the cells have been numbered, and now we need to take a look at the function once again, and we have the don't care elements 2 and 4. Okay, so we're gonna put 2 and 4. Okay, we're gonna put a cross for the don't care elements. The cell number 2, we put a cross, and then again we had the cell number 4. So there you go. So with crosses we just denote the don't care elements. Okay, so it's pretty much the same form of indication used for both the SOP and the POS forms for the don't care elements. Okay, so now that we have just filled up our K-map, so we're just going to group it up. Okay, so now we can see that we're gonna get a we're gonna get a quad over here. Alright, so you should always keep in mind that whenever basically we're having a K-map, okay, whenever we're having a K-map, so with don't care elements, of course, we're gonna use up the don't care elements only if they are required. I mean, you have a certain number of don't care elements. We have 2 don't care elements over here. So if it appears that we can just group them up together with the other elements that are valid elements that are present along with the don't care ones. So if we can just group them up together to form a quad or to form a duplet, okay, only then we shall use them up. Alright, so it's not a necessity that we have to use the don't care elements. It is nothing like that. If you want to, if you see that including a don't care element just reduces, or rather just helps in grouping up, or rather helps in just creating more groups together, okay, then only you're gonna use them to just group up with the other elements concerned. Okay, it's just that these elements that they don't cares, they are just present as a byproduct. They are certain elements that don't affect the system operation even if they occur in the function. Okay, so it's not a necessity to use the don't care elements if you don't require them to reduce the function. Okay, so since we can see over here that for the cells 4, 5, 12, and 13, we can see that including this particular don't care element in group, I mean in the cell number 4, it just helps us to create a quad, so we're just using it. Okay, so other than that, we got cells 6 and 14 adjacent to that of cells 4 and 12, so we're going to create another group using the same don't care element over here. Alright, so apart from that, we have one over here left all alone, so we're gonna not keep it alone all the time, so we're just gonna group them up together. Okay, so now all the valid elements, that's all the ones that we have here, have been covered in groups, and this just one don't care element in cell number 2 just stays there alone. So it's not a necessity to group it up together because we have all the ones covered up in the group. So it's not a necessity at all to include this don't care element. So we won't just include it and increase the number of groups unnecessarily. So now this is done, and we're gonna go and find out the reduced expressions for each of the groups concerned. So first of all, we're gonna go for group 1. So for group 1, that is this particular duplet over here. So what we can see over here is that we're just gonna, since this is a product of sums type of K-map system over here, so we're gonna basically arrange the variables as certain products and then take their sum together. And of course here, as I said, 1 represents a non-complementary quantity, I mean a variable, while 0 represents a complementary variable. Okay, so here we have for the very first duplet over here, we're gonna get a bar, b bar, c bar, d. Okay, so I'm just gonna write it up together. So this is a bar, b bar, okay, and then c bar, d. That's for cell number 1, and then for cell number 5 we got let's see, a bar b, we got A bar B, C bar D. Okay, now if we just reduce this thing, we're gonna get, let's just check out what is common over here. So we can just get to see that we have A bar, C bar, and D common. So we can just take them up as the common terms. So A bar, C bar, and D. So this is the common term over here, and the rest is just reduced by De Morgan's theorem. Okay. So now that group 1 is done, we're going to go to group number 2. Okay, or rather, yeah, that the group number 2 is the pink one. That's the pink quad that we have over here. So for group 2, we are going to get, well, let's see what we are going to get for group 2. We are going to get, well, yeah, A bar B, C bar, D bar. Okay. So we have here first A bar B, C bar, D bar, and then we're going to get another one. Okay, so this is for cell number 4, and then we got, well, cell number 5 over here, which is of course A bar B. There you go, A bar B, and then we got, well, C bar D. Fine. And then we have 2 more terms coming up. Now cell number 12. So cell number 12 is of course A B, C bar, D bar. Okay. A, B, C bar, D bar, and then again for cell number 13, let's check it out. Okay, we got, well, A, B, so let's pull the page up. Okay, A, B, and let's check it out once again. Okay, C bar, D. Alright, so now if we just try and reduce this thing, we can get to see, we'll just pick up what is common in all the 4 of them. So now we can see here only the term BC bar appears constantly common in all of the 4 terms. So upon reducing this entire thing using De Morgan's theorems and the basic laws of Boolean algebra, we can get this term BC bar. Okay, now for the third group over here, that's the green quad. Okay, that's group number 3. Okay, so if we just take a look over here, so we're gonna get, well, okay, let's see, we're gonna get, all right, A bar B, C bar, D bar, plus that of, let's take a look again. Okay, we are gonna get, well, A bar B, C, D bar, and once again, okay, now, yeah, there you go, and finally we got, well, A B, C bar, D bar, and plus that of the last, so that's the cell number 14. Yep, there you go, we got, well, yeah, A B, C, D bar. Fine. Now again, we're going to check out for the common terms over here. Now we can see here that the terms, okay, let's check it out over here. Now the terms B and D bar over here, they appear constantly common in all 4 of them. Okay, so the common term that we're going to get over here is B, D bar. Okay, so that's the reduced expression, and the rest is just, well, equal to, I mean the rest is all, well, reduced equal to 1 by the laws of Boolean algebra. Okay, so now that we have all the 3 reduced components, I mean expressions over here, so our final expression that we are going to get as such, now the final expression right over here is given by this symbol F min, and that is obviously equal to the summation of all these product quantities that we have got as a result of reduction of all the 3 groups. So we're going to get, well, yeah, B D bar, okay, plus that of B C bar, and then we're going to get, well, A bar C bar D, plus that of A bar C bar D. Okay, so here we have finally obtained our minimal reduced expression using the SOP system of reduction. Okay, so here we have just successfully been using the K-map to reduce the expression, and now our problem statement again says that we need to well, implement the reduced expression over here in terms of universal logic. Okay, so now we can see here if we are going to basically utilize the universal logic in order to implement this particular expression using a digital circuit, then we are going to use either the NAND or the NOR gates. So since we have this expression in the SOP system, so it's always easier to use NAND gates in order to build up the circuit concerned using this minimal expression. Okay, So let's just check it out. Now we need to basically convert this particular result in the form of NAND logic. So let me just write it down once again. So BD bar plus that of B, C bar plus that of A bar, C bar, D. Now let's just put two big bars over them, okay, so that they just remain neutral as such. So it's just a basic Boolean algebra, so it's not a big deal. So now if we just take if you just take a look at the expression inside and its bar on top. So from De Morgan's theorems, okay, we get BD bar whole complement multiplied with BC bar whole complement multiplied again with A bar, C bar, D whole complement. So this is exactly what we are getting in the NAND logic. Okay, so this is our respective NAND logic. So we are going to use this particular result that we got here in terms of NAND logic and implement this one using the NAND gates. So once again, we're going to need NAND gates. Okay, so we need 1, 2, and 3 NAND gates over here. So there you go, 1, okay, and then you got 2, and then finally 3. All right. So what have we got over here? We got BD bar and BC bar. Okay. So this is, let's say this is C bar, and let's say this is D bar, and we got a common line over here which supplies the B variable. And again we got A, C bar, and D. Okay, so we got D over here. Okay, we need a C bar. Okay, and we need an A. So we have an A over here, and then we can just pull up a line from over here and feed it to the third NAND gate. Okay, and then whatever the outputs are, the outputs obviously from this particular gate would obviously be B, C bar whole complement. Okay, so that's exactly these results that we have exactly obtained over here. So we're just going to take each of them, each of their outputs, and then we can see that these complementary values have again been multiplied with another complement. So basically it's quite easy to understand that the outputs of each of the gates are basically needed to just pass through another NAND gate, okay, so that we can just get the result. Okay, so whenever we do this, we finally obtain our required expression. Okay, so we are going to get this particular expression F min that we have over here using the universal logic. That's the NAND logic that we have just basically used over here to construct the circuit. Okay, so that's all from this tutorial, and we're going to wrap up our discussion right over here. I think that it's been a good experience for you all to watching this tutorial. So it's just a short goodbye for from here on, and just keep watching.